Okay, cool. Let me share my screen. Okay, so this is my second attempt at presenting this paper called Practical Markov Chain Monte Carlo. I'm actually not going to present the paper again, but I'm going to present parts of the paper this time, and then we'll be done with this. It's a really cool paper and it's really interesting, but I think the level of mathematics in this paper, it requires you to have like a very in-depth understanding of the fundamentals of statistics, and then probably also just a good amount of experience with MCMC, which I think is an unrealistic expectation of, like, I don't have that, and a lot of the I'd be surprised if most people here have it. So instead, I'm going to present some more fundamental concepts that I think are important to understanding the paper. Because I want you to, I'd rather you take away some fundamentals from this presentation than going through the paper word for word. Before I do that, I want to give a quick introduction into, like, I'm gonna review some stuff from last time, just so we're not doing a ton of context shifting. So Markov chain Monte Carlo is a method. Well, where do I start? Okay. Markov chain Monte Carlo is a method that allows you to sample from a distribution without actually having access to that distribution. Instead, you might only have access to, I'll show that really quickly. I think it's, instead of having access to a distribution P of X, you might only have access to F of X, which is it's the distribution, but where you don't know what the normalizing constant of the distribution is. And usually, if you don't know what it is, it's because you don't know how to integrate this function here. This situation pops up a lot more than you might think. It can be used as part of optimization problems. Actually, they say it in the paper, all the different places where it can be used. It's mainly used in Bayesian applications, but I think it's better in the conclusion. What's going on? There you go. Is useful in Bayesian likelihood and frequency statistical inference. Oh, it doesn't. I thought it would give more. But anyway, you can use it in optimization problems and just like problems where you're trying to characterize a distribution. It's generally useful when you're trying to do statistical inference and you're in the situation that we were describing before, which comes up a lot more than you would think. What I would recommend is, as you guys go through your work, if you're ever coming up to a point where you're trying to estimate a distribution, maybe check if the Python package you're using or whatever other library under the hood is using MCMC, because there's a good chance it is. I know that Gaussian processes, like one of the ways that Gaussian processes, for example, are estimated, is often using MCMC. So it's a generally useful technique, and that's why I wanted to do a paper on it. And so there's a lot of like considerations here, because the cool thing about it is, like I said, you can get samples of a distribution without knowing the distribution. So it's actually a way that you can estimate the distribution, like through calculating statistics without knowing it. But there's a lot of considerations here about what needs to happen in terms of how you perform MCMC in order for you to actually estimate that distribution. And in fact, this paper goes one step further, which makes sense because it's necessary. And it's like, I don't only want to be able to estimate like summary statistics of the distribution. I want to get an idea of how right or wrong I am based on the samples I have, which makes sense because if you calculate the expectation of a distribution and say the expectation is 100 and then you find out that your error is like 100,000, then it's not a very useful estimate of the expectation and you can't really use it for anything. So yeah, this paper focuses a lot on how can you estimate the Monte Carlo error with MCMC, and we'll get into that a little bit later. But wrong side. So for this paper club, I'm going to go through a couple of different things. So last time we said that one thing that would be useful to cover this time is so the way that Monte Carlo Markov chain Monte Carlo works is that you construct a Markov chain, which is basically you sample and then you use that sample to calculate sample your next sample and so on. And this converges to the distribution that you're trying to estimate. And the reason why it converges is because the Markov chain is formulated in a way where its stationary distribution is the distribution of interest. So I just wanted to briefly review what a stationary distribution is. So, and here are some examples. So say like your Markov chain is just integers for real numbers, let's say real numbers. And you could think, probably it's converged over here because we just keep seeing the same two numbers over and over again. And that could mean that it's converged to its stationary distribution. Here's another example. The stationary, you know that it's converged to, or when the chain is converged to its stationary distribution, the frequency of elements in the chain doesn't change over time. So if you took 1,000 more samples, the probability of any one of the values that you saw wouldn't change when you recalculate them. So one question that people often want to know when they're performing MCMC is, how do I know when the chain that I've created has converged to the stationary distribution? Because if I know it's converged, then I can start using those samples to calculate the values that I want about the distribution that I care about.
One quick question is that not maybe a slightly misleading statement, right? When you say a stationary distribution, when we know how Gibbs sampling works, right? So if you have any space, you sort of do hops in that space, and you are naturally staying relatively close to where you started, hop by hop, and only over time you move away, right? So you wouldn't necessarily expect that even if you are in a stationary distribution, that you can take any two samples from it and they would be samples from the stationary distribution, because these samples, if you're not very careful, are very highly correlated.
Yeah, well, that's a really good point. And it actually leads to the topic after this one, which is, in my opinion, like the bulk of the paper talks mainly about that problem. So it's a really good thing to point out, that samples that are close to each other, or sometimes even far away from each other, are highly correlated. And we'll talk about why that's important, or why that's an issue. But
so yeah, I think ultimately the question is, how do we get independent samples? Because if you think about, if you want to know the mean of a distribution, and if you have 10 samples, your uncertainty across your mean is already smaller than the standard deviation of your fundamental distribution, meaning that for practical purposes, that's for most ever, you need anything, you need 10 independent samples are often enough of whatever it is. So getting these 10 is the hard bit.
Yeah. So yeah, as Arvid pointed out, it's not only that you need the chain to converge to the stationary distribution, but you have to find a way to take samples from the chain which are as independent as possible in order to estimate summary statistics. So there's two conditions. Right now I want to focus on the converging to the stationary distribution, and then we'll focus on the second one about like the correlation between samples. So one of the primary methods, I'm just going over it really quickly, for testing convergence to a stationary distribution is you sample multiple Markov chains that all have the same state, that are constructed to have the same stationary distribution. And then you calculate the square root of the variance between chains divided by the variance within chains, which is like the mean of the variance within chains. And r hat is, this value is lower bounded by 1. And if you see that r hat is greater than 1.1, that means the chains have not converged to the stationary distribution. And the closer to 1 it gets, the more likely they are. There's no like foolproof way of proving that it's converged, but this is like a metric that you can use that suggests convergence. So it's kind of the idea that there's like an agreement across chains about the variance. And here's the Medium article that I read that talks about this, if you're interested. So this is how you could test for convergence. But as Arvid pointed out, that's not enough. You can't just converge to the stationary distribution, because if your samples are highly correlated with each other, you can't really do much. Now, that brings me to a really important topic from this paper, and fundamental concept in time series analysis of stochastic processes. Or stochastic process analysis is probably better, because you can have, what is autocovariance? In probability theory, this is from Wikipedia. In probability theory and statistics, given a stochastic process, the autocovariance is a function that gives the covariance of the process with itself at pairs of points. So autocovariance, the variable that you usually see in the literature, is gamma. And it's the covariance between two points that are separated from each other. So for example, if they're one step away from each other, then it's autocovariance step size 1, gamma 1. If they're 2 steps away from each other, then it's autocovariance with step size 2. And you can go in both directions. So you can have like autocovariance with step size minus, or with step -1, which might not necessarily be the same as the forward direction, but I think in a lot of cases it is. But like, just to give you guys an idea of how this might be calculated, say you're trying to figure out the autocovariance with step size 1, then what you would do is you would you'd have say you have a chain that's like 1,000 points. Then you would take you'd have 999 pairs with which to calculate autocovariance, because you just need, each pair is 1 step away from each other, and so you can just use each one of those to calculate your autocovariance, and that's just calculating the covariance between those 2 pairs of samples. So that's a really important concept that you see a lot in stochastic processes. And you see an example of it in the paper, where they describe like a synthetic process that they create, and then they show you this plot of autocovariance. There we go. So you can see that like the autocovariance with step size 1 has a much, much higher value, and it decays exponentially and then kind of stays around 0 as the step size increases. And that's kind of what you want for your autocovariance.
And one quick question. So that is a property of the process that generates the samples, but not a property of the distribution that you are sampling.
Yeah, because the distribution is fixed.
Yeah.
And this is more, as you said, this is about the it doesn't have autocovariance because the step, maybe the distribution you're estimating is its stochastic process itself, but then the Markov chain is also a stochastic process, and this is the autocovariance of the Markov chain.
Yeah, gotcha. Thank you.
So they would be separate. So yeah, we just talked about autocovariance, and now let's talk about Markov chain mixing, because it relates to that, and that's a big topic in this paper. So Markov chain mixing, what is mixing? Mixing refers, this is from the paper, mixing refers to the dependency between like step xi and step xi plus t, where t could be like 1, 2, 5, whatever. And it says rapidly mixing means the dependency decays rapidly as a function of t. Slowly mixing means that there is an appreciable dependency over hundreds of iterations. So if we look back at this, this is a good example of rapidly mixing, where you see like an exponential decay in the autocovariance as the step size increases. I guess probably a slowly mixing one would be one where the line is more like linear, or maybe even like what is it? You get what, I think you get what I mean. And so this is the other condition that you need to be able to use the samples in your Markov chain, which is that the Markov chain is mixed. And that means that the way that, I think it's in the next slide. Okay, I'll actually do this first, and then I'll go back to the other one. No, sorry. Mixing is measured by autocorrelation, which is autocovariance divided by a constant. So you can actually use autocovariance instead of calculating the autocorrelation in order to measure mixing. And yeah, I think it should look something like this. This is what you need to see when you calculate the autocovariance over different step sizes in order to feel like this is a well-mixed Markov chain. So like, why is that important? Mixing is important because, so when we're trying to characterize a distribution using statistics, we rely on a lot of different theorems. Like one of the main ones is the central limit theorem, which we use for estimating the mean of the distribution. And one of the main assumptions of the central limit theorem is that the samples have to be independent. And there's extensions to it, to our case, where they have to be like quasi-independent. So maybe two samples that are near each other have some kind of correlation, but as you get farther away, they have very, very little correlation. Then you can start using these samples for estimating statistics of the distribution. So that's why it's really important that these samples are mixed as well as converge to the stationary distribution. And we'll look at some like math related to the central limit theorem in a second. Yeah, and they even say in the paper, a chain may converge to its stationary distribution, but still be mixing too slowly for Monte Carlo, which means that you can't use it because it's not mixed well enough. So just as a final thing before I go into the paper, I wanted to talk about burn-in and how it relates to all of this. So we've just talked about like how you might test for convergence and how you might test for mixing. In the paper, and for both of those, what the goal is to do is to like figure out, okay, when can I start using the samples that I've taken and reject the ones before it in order to calculate the statistics that I want to calculate. So that's the burn-in period. And the author provides this rule of thumb that you can reject like 1 to 2% of the samples. And all the examples he uses, they're taking at least like 10,000 samples. I bet if you were taking 10, you wouldn't say reject 2 of them or 1 or 2 of them. And yeah, the other way that he suggests doing this is to measure autocovariance of samples to determine whether the samples are mixed. What I found interesting about that is that as a practitioner, he seems to care a lot more about mixing than the station, whether the distribution is stationary, has converged to the stationary distribution. So maybe there's some result that I don't know about that says that like you'll converge to the stationary distribution before you've mixed well. And so really, if you've mixed well, then you know that you've converged to the stationary distribution. Okay. So we've talked about these two things. Let's talk about sample statistics and the central limit theorem. And here I can actually start showing you the paper, finally.
So I think about the
Mhm.
worrying about the stationary distribution, I think there's always this assumption of ergodicity, is essentially that you can get to any part of the chain in reasonable time.
Mm.
It turns out, I think that is where in practice a lot of these methods actually break, where also your stationary checks can potentially break, that even though you see your autocovariances are dropping off and so. But if the starting point of your chain is important, that you sort of freeze into local stationary results, then of course you can sample a lot from that one chain, but you will never get a true estimate of the full distribution because you're sort of stuck. And I think that is where when it was practically quite difficult, especially in high dimensions, right? That your Markov process is sufficiently broad that you can actually jump from one part in space to the other in reasonable time, which is why you have stuff like annealing or so, where you sort of make jumps unreasonably high. You don't get the right distribution, but then you sort of cool it down, and eventually you get something that looks like the real distribution again.
Mm. Yeah, both. I guess I took your comment as saying that you do have to worry about whether the
Yeah, I think that is sort of
the chain that you're. Sorry, go ahead.
Yeah, so I think that is sort of the assumption that is being made in the paper, that your whatever process you choose, you sort of assume that it can get everywhere in that process. Once you're reasonably sure of that, then I think a lot of these covariances, autocovariances make perfect sense. Otherwise, they of course can be misleading. I think that is the.
Yeah, I think like it even says it over here. I think when you can get from one part of the to like your state space to any part of the other, it's when it's an irreducible Markov chain.
Yes, that's correct. Yeah.
And so I guess it's assuming that the Markov chain is always irreducible or something along those lines.
Yep.
So talking about the central limit theorem and sample statistics. So over here is the classic equation for calculating. Actually, this should just be x if you wanted to calculate the mean. But see, you're taking an integral over your probability space with respect to some function. So that's calculating the expected value of that function. But if your function is just identity, then you're calculating the mean of the distribution. And so, but anyway, we'll take the more general case of you're trying to calculate the expected value of a function with respect to your probability space. Trying to think if I can think of a good practical example. Maybe a really simple one would be like you commute from 8 to 9 every day, and you want to see like whether you're going to get wet or not. So the distribution would be you're integrating over is like the likelihood of rain, and then the function would be like if it rains then I get wet, so it'd be 1 if it rains and 0 otherwise. But anyway, so you want to calculate your expected value of some function with respect to a probability space by doing this integral. Well, usually this integral is intractable. You don't know how to calculate it except for simple distributions. So instead, you can use Monte Carlo integration to calculate it, which is when you take many samples from your distribution and then calculate the value of the function and then average over them. Now, this is the Monte Carlo estimate here. And the first version of the central limit theorem, there's others, assume that the samples that you are taking are independent from each other. And that's like an important assumption. And so the whole idea of the central limit theorem is that, like, the important part of it is this equation here. So what is this equation saying? It's saying the difference between the actual mean of the distribution that you're estimating and the sample mean, the one you've calculated, multiplied by the square root of n, which is the number of samples you've taken, converges to a distribution over, which is a normal distribution with a variance equal to the variance of your of the underlying distribution you're sampling from. So there's a couple of things that I wanted to point out about this equation. I think one, which is a little bit less intuitive, is that the error of between your sample mean and the actual mean is a distribution. And actually, the sample mean is distributed. You can think of like the sample mean that you've calculated as a sample. And say you did 100 other samples instead of the 100 you did, you would get a different sample mean. And so that just shows you that because you're sampling in order to get it, that like even the statistics that we calculate to estimate a distribution have a distribution themselves. And it's important to, well, the reason why the central limit theorem is so powerful is because you know that the error, like the variance of the error between the sample mean and the actual mean decreases in size with the square root of the number of samples. So if you take 10 samples, I mean, if you take 100 samples versus 10,000, that means that your error, like the variance in your error, is 10 times smaller. And so this allows you to actually estimate the error in your distribution based on the number of samples. And you know that like as you have more samples, the sample mean is converging to the actual mean. Yeah. Now, as I said before, all of this is and I'll just say that like the variance divided by square root of n. So sorry, the standard deviation just divided by the square root of n is the standard error, which is like you can use it to create confidence intervals around how right you are with your sample mean. I think it's also called the Monte Carlo error when you're using Monte Carlo to do the estimate. And a big part of this paper is how do we estimate the Monte Carlo error? Like, how do we do it? And the theory behind how you could do it with MCMC. And the big issue that they have to tackle, and the reason why it's a complicated issue, complicated thing, is that in Monte Carlo, Markov chain Monte Carlo, the samples are correlated with each other because you're using one sample to estimate the next one. And consequently, you have to use some other sophisticated math in order to calculate the variance in order to calculate the standard error. And you want to know the standard error because you want to know how right or wrong you are. Yeah. So we're talking about Monte Carlo and the central limit theorem. Yeah, one big thing, I know I'm repeating myself, but when I first took a statistics class, that it was actually pretty big new idea to me that statistics are also follow a distribution, and they're not just like some deterministic value. Given the samples, they're deterministic, but because you're sampling to estimate a statistic of a distribution, it's distributed itself. It's also distributed itself. Okay. How much time? Are we doing okay? Okay, we're doing good. there's only one last thing I want to cover. I know there's a lot more in this paper, but I just want to cover what I consider to be like the crux of the paper. And that is how you can calculate the Monte Carlo error for Markov chain Monte Carlo. As we said before, the big issue is that the samples are correlated with each other. And okay, there, it looked blurred to me. And so there's a lot of complicated terminology here. Like they don't actually say the word autocovariance, but afterwards they do. I think, but it's just because I want to be as general as possible with the proof. But assume that gamma is the autocovariance. And it's saying that they're equal to each other, okay? So it's saying for a reversible Markov chain with a stationary distribution P, some function which is square integratable, and then it's saying this is equal to gamma. So the covariance of this function, I see why they're doing that now. Sorry, my bad. But anyway, let's talk about the covariance. So just assume this is autocovariance with lag t. So t could be 1, which means it would be step size 1. Lag could be 2. Lag t could be 2, which is step size 2. And the really important result is over here. This is like the main thing, which is that the variance that you care about. So the variance that of the error between the mean and the sample mean, or like the expected value of the function and the actual value of the function, is normally distributed with variance sigma squared, but sigma squared is the sum of the autocovariances of your distribution. If sigma squared is finite. So if this infinite sum converges to a value, then it's normally distributed. And so the crux of it is if you can calculate the autocovariances, like and a large number of them, so step size 1, 2, 3, I don't know, up to like 100 or 1,000, then you can calculate you can estimate the variance, and you can calculate the standard error, so you can know how wrong you might be in terms of your estimated mean.
Hang on.
And then, yeah.
So, so n is small n is your sample size, right?
Yep.
Yeah. So make n bigger. That is the left-hand side. We're saying that becomes more or less Gaussian as the number of samples get bigger. That is fine. But now on the right-hand side, we have the sum over the autocorrelations, which are not a property of the function you're approximating, right? Or the distribution you're approximating, but it's a property of the process itself.
Yep.
Isn't that weird that the sigmas? So it just means that this sigma is not the same as the sample variance or standard deviation of your raw distribution, right?
Yeah, I think that's how I interpret it too. They call this the asymptotic variance, or like the term he uses to I guess to distinguish it is he starts calling it later on the asymptotic variance. But yeah, so it means that it's no longer the variance of the distribution you're trying to estimate. Instead, it's this sum of your autocovariances.
Yeah. Interesting.
Yeah, I think over here they talk a lot. They talk about like spectral representation and spectral theory of bounded self-adjoint operators, which honestly I don't know anything about.
The samples are they supposed to be taken independently, or is there already like the time between samples taken into account, or do we know how we get to this sum over gamma t's? That seems kind of funny.
So I think that the assumptions are that it says it somewhere over here. I think it says somewhere that you have to already have converged to your stationary distribution. And also you have to be well mixed. So the samples aren't independent of each other because for MCMC they never will be. But if they're well mixed, that means that like the dependence between them decays exponentially with the number of steps. And I think those are the two assumptions that are required in order to have to be met in order for this result to hold. And also like all of these.
It's still a bit funny that it then depends on gamma. You would think that if they are truly independent, this gamma value doesn't matter, right? Because you're essentially in the exponential regime where gamma is more or less zero.
Well, gamma, it's not that. So if you're in the well mixed regime, it's that you're because the way that MCMC works is that it uses the previous sample as the mean of the distribution you sample from to get the next one. So there will always be a high correlation between the like autocorrelation step size 1. But the fact that it decays exponentially means that probably like the first couple of terms will be enough to calculate the variance, this variance that they're talking about.
I see.
That's my understanding. I don't claim to be an expert here. Yeah. Actually, I won't go into the spectral theory, but I find it interesting. So yeah, that's actually that's all I wanted to, because I feel like I covered a lot, and maybe and this paper actually has no experiments, so there's no results to really show you. But that's the main thing I wanted to talk to you guys about, like the relation between autocovariances and how it relates to the standard, the variance of estimating your value, the value that you care about, and then how you can use it to calculate standard error. And there's tons of different ways to do that, which is what the estimating variance section is about. I don't know why it's taking my computers. Okay, but the long and the short of this paper is like the only thing that this author suggests conclusively is use one long chain in order to take samples, and then the rest of it is like, well, it depends on your problem, and like you don't know, like it's really hard to know whether your chain has mixed. It's hard to, well, he doesn't really talk about stationarity, but it's really hard to know if your chain is mixed. You have to try a couple of different sampling methods in order to determine that. There's no like clear answer for what's the right way to go about it. So this paper is more of like a discussion, which I think if I were using MCMC a lot, I would find really useful to decide which method to use. But there's a lot of results here, which I don't want to go into too much detail about, because like I don't know much about spectral representations of operators and stuff like that. I can kind of guess based on what's being said here, but yeah. So I hope that wasn't, I hope you found something out of there that was useful, and that you might use MCMC sometime in the future. Yeah, interesting result. That's fundamental to the paper, and interesting paper in general. Just very heavy on statistics. If anyone has any questions, I'm happy to try to answer them now.
So I can use the autocorrelation to essentially set myself a distance between samples that I should take to sort of guarantee that they are independent enough.
Yeah, so that's actually something that they talk about as one of the methods for estimating the variance, which is, no. Subsampling the chain reduces the autocorrelation. If every mth interaction is used and the rest thrown away, this produces another reversible Markov chain with asymptotic variance, this. Yeah, you could. For some reason, later on, he argues that there, it's, okay, I can read down here. Here's like a bound on the asymptotic error for doing that. And it says, Okay, so his point is you can do that, but if your cost of sampling is too high, it's not worth it.
Yeah.
In this section. So yeah, but you could do that. You could just take every 100th sample. It's funny now, for this this paper was written long enough ago that I bet like it's way easier to sample now, and like a lot of the results here where they're struggling because they don't have enough time or it takes too long to get data. Probably now it takes no time at all.
Yeah, I was actually reading a paper the other day. It was on reservoir sampling. So you have a very, very large data set, and you want to get a number, say 10 independent drawn samples from this very, very large data set. And it's a surprisingly difficult problem. So the guy, the paper writes about how you only want to traverse the tape on which the data is stored once, and literally calculates the number of calls to the random number generator you have to make in order to get it faster, and you split it up by several orders of magnitude. So instead of sampling 10 to the 5 items in hours, it does it in seconds. But nowadays, of course, just take data frame sample and it's right there, and you don't ever think twice about it. But it's kind of cool because it's surprisingly difficult to get a random sample that they don't have a bias, and like having certain, say if you start from your tape at the beginning, you load them in one by one. You want to essentially resample them in such a way that there's the chance of a sample persisting long enough in your data set gets lower and lower, so that even though you don't know how large the reservoir is, eventually later on, just by pure chance, you're more likely to get a new sample in than out again, and it's quite fascinating.
Yeah, I do feel like a lot of the underlying math for what we do these days is hidden away in a way where we don't have to know it. But I think it's nice to know.
It's actually still used. But so I got to this paper because of another paper on reinforcement learning, where they use reservoirs to then sample back, regurgitate samples from past runs, and actually that becomes quite important, that you don't have any biases in there. Otherwise, your learning gets unstable or anything. But yeah, nowadays the papers nowadays are so much easier to understand in some ways, because it's often just like, oh yeah, we tried this worked, and here's a nice graph. Whereas back then you had almost like a degree in statistics to follow any of the argumentation.
Yeah, I wonder if we'll get back to that, because I do feel like in terms of publishing papers in the top tier conferences, they used to accept, in machine learning at least, they used to accept papers that had a lot less math, and now they kind of want there to be math in there. Yeah.
Nice.
Cool. If no one has any questions, thanks for coming. I promise that the next paper I present will be a lot more accessible. But we have Jared presenting next week, so you're done with me for a while. But yeah, everyone have a good weekend, and thanks again for coming.
You too. Thank you very much.
Thanks, Peter.
Cheers. Bye.
Thanks.